All right, folks, let's get started today. So, as I'm sure you noticed, today I'm showing you guys a picture that is not a planet. This is, of course, the sun. So we don't really talk about the sun much in this solar system class. If you want to learn about the sun more, you should probably actually take Astronomy 122, which is the stellar physics class, or take a quarter of physics and then join my upper level class. Then you really learn about the sun. And the reason is most of stellar physics is really not applicable to planets. So outside of our sun, we talk more about the planets in our solar system class. But today we have a notable exception because, as you can see, the sun is actually, it's a ball of plasma. It's a very dynamic system, and it has bits of it that can sometimes get ejected off the sun in various mass ejections. They can travel to Earth. We get particles from the solar wind from these ejections and from particles from the sun. And we're going to discuss today how those affect us on Earth and everything like that in our day-to-day lives. So yeah, we're going to head to the new material now for the rest of the lecture. So what we're going to talk about today is Earth's magnetosphere, which is our magnetic field and all the good things it does for us that, we should think it daily, but we never think about it. So the Earth's magnetosphere, first of all, magnetism. What are magnets and how do they work? So we have our magnet. It has a north and south pole. And what we have are magnetic field lines that connect the North Pole to the South Pole and point toward the South Pole. So every magnet, you can't have a single magnetic field. You always have a north and a south. And this is what those lines look like. They go outward and reconnect. So what we have on Earth is we, of course, have a north and south pole magnetic field. Compasses work on Earth. If you have a compass out in the forest, you can use it to figure out where you are on our planet. So here's a question. I just told you that there's the field lines. They connect the North Pole to the South Pole and point toward the South Pole. So here's the diagram from the previous page. Under the North geographic pole, so where Santa and the elves live, is there a north or south magnetic pole based off of this diagram? Okay, yes, so the souths have it. These field lines in this diagram are pointing toward the north magnetic pole, so then that would be the equivalent of a south magnetic pole. It's purely a convention thing, it turns out. So it's not, yeah, but we still call it conventionally the north magnetic pole in the north, the south magnetic pole in the south, just to keep things confusing. But basically, if you see a diagram, look the direction that the arrow is pointing, and that's how you know what is a north pole, what is a south pole. The other thing to note about the magnetic poles is, for the record, it's first of all not exactly at the North Pole. It's not where Santa is. It's actually kind of up toward north of Canada now, and it actually varies quite a bit over time. It meanders. So this is a diagram of how it's changed over time, and it's actually really been changing fairly rapidly in recent years. It's actually going further north. When I was a kid, we learned that it was up, somewhere in the northern territories of Canada, and now it's actually as close to the North Pole as it's been in a very, very long time. This doesn't usually matter for most of the planet. It does matter if you're, say, in Alaska and you try to use your compass in the forest, pointing toward, your compass is pointing toward this North Magnetic Pole, not the true North Pole. So you do have to take that into account when using our magnetic field for navigation like that. So what causes magnetism? It is created by the motion of electric charges. So what this means is if we have an electromagnet, for example, and it will create a field, then you will have lines that are created because there's electric charges moving through this system. So why does this matter for the planet? So we believe our magnetic field is due to what is called a dynamo in the core of the Earth. So the core of the Earth, as we mentioned before, is basically a giant ball of iron. It's actually very, very large. It's over 1,000 kilometers across. So it's comparable to the size of the moon, actually. And there is heat and a lot of rotation. We know our Earth is rotating every 24 hours. So once a day, this dynamo is rotating. And the convection and rotation sets up basically what is the equivalent of a giant coil in our planet due to this liquid ball of iron. And that is what creates our magnetic field. So what this dynamo then does, beyond just having us have compasses that work on Earth, is create a magnetosphere around our planet. So we don't usually think about magnets and magnetism as being important, but it turns out on very large scales, they are actually incredibly important. On a galactic scale, for example, if we did not have a magnetic field in our galaxy, the galaxy would actually collapse into a flat pancake instead of the disk that it is. That's just kind of one of those astronomy trivia facts. But on Earth, what ends up happening is we have this thing called the magnetosphere, which shields our planet. So we have the Earth in the center. We have the interaction region where there's particles coming in. There's the Van Allen belts. So that's a very high radiation zone because that's where a lot of these particles are moving back and forth. Astronauts should definitely not hang out in the Van Allen belts. They would get a lot of radiation if they did. And then we have the magnetospause, which is roughly where the magnetosphere equals the solar system's magnetic field, and everything is in equilibrium. The reason this is important is we have charged particles that come from the sun. There's a couple of them every square meter just as a normal course of events. We'll discuss exceptional events in a minute. And what happens to these particles is they then funnel along the magnetic field lines until they strike the atmosphere, so the upper bit of this magnetosphere, and they will cause those molecules to glow. I have a video to show you guys what this looks like. So here's our Earth, and we have a steady stream of particles, which are primarily from our sun. As I said earlier today, the sun is a giant ball of plasma, so there's just particles that are constantly escaping its surface. So in this visualization, you could see the particles quite clearly. And what you start seeing is if you're looking at their direction toward Earth, they're being deflected, right? They're not coming straight toward our planet, and that is due to our magnetosphere. You can now see the magnetic field lines in this animation, showing more clearly that, you know, some particles will come closer. They're going to be channeled into the magnetic field lines in this system. But overall, we're very nicely protected and cocooned from the majority of anything that could come from solar particles and solar radiation. Lucky for us. So the biggest thing that most people have heard of before that is caused then by our magnetosphere is the aurora, or the northern lights or southern lights. And the aurora come from the solar wind. So the solar wind, if we have, you know, here a very simple schematic, we have our solar wind particles coming inward. They get trapped in those magnetic field lines in the magnetosphere, and they get funneled toward the north and south magnetic poles. And this will create the aurora borealis, or the aurora australis. So who here has seen the northern lights or the southern lights? Usually most people know. Okay. Does somebody remember when that was? Yeah. Yes. So there was a major solar storm in May of last year. On May 10th, 2024, we had the biggest solar storm in decades on our planet. I actually happened to be completely coincidentally that evening flying California to Boston, so cross country. And you know, when you get on the plane and your friends in Europe who live in like Florence, Italy are posting Northern Lights pictures that you should get a picture on the north side of the airplane. And then, yeah, even the pilot was like, we'll probably see Northern Lights. They showed up around Chicago. And then basically for 2 hours is just a complete curtain of light across the entire sky. I'd never seen anything like it. The thing that was also kind of crazy to me, and this shows I'm an astronomer, but I was just staring at this the entire time because it's an incredible light show. Most people, when the pilot announced it, looked for like 30 seconds and then went back to their tablets. And I was like, oh, but guys, this is so cool. It was also an unusual one. So it was seen in Eugene. Were you around here? Or? Okay, yeah, so Washington. I mean, I had friends in Mexico who posted pictures of Northern Lights that night. It went, you know, basically so far south that a lot of people who had never seen the Northern Lights before did. It was also unusual because it had a lot of different colors. So normally Northern Lights, if you look at them, they don't actually have much color to our eye. Like you'll see pictures that have amazing colors, but our eyes are not as sensitive. So usually just looks whitish. I took this picture. I swear it actually looked this red and purple. So it was just a really, really exceptional event. The other thing that was just, kind of a brag moment for me is the one time I've ever been on CNN because I posted the pictures to, I think it was still called Twitter at the time. I don't remember. And then CNN was like, can you come on as an astronomer and tell us what's happening? So that was fun. The other one, though, is so you can see beyond the northern lights, the Aurora Australis. We don't usually think of it because not that many people live down there, but it does exist. So this I took in June 2019. NASA had a instrument at the time called SOFIA, which was basically they took an old Boeing 747 and cut a hole in the side of it and then flew around with a telescope above the atmosphere. The reason you do that is at infrared wavelengths, most of the infrared light is blocked by our atmosphere. But if you go up to, 30,000, 35,000 feet, you get about 99% of that infrared light, which is, more expensive than a lot of things you can be doing in astronomy, but cheaper than a space telescope to take a giant Boeing 747, refit it. And then this is basically the control room part. Here's the telescope on the other side. And then, so what they did, it stopped a couple years ago, but they would fly out of normally California, Moffett Field. But once a year, or every other year, they would go down to New Zealand to be able to study the southern skies. And one of my PhD advisors, he was a PI for one of the instruments, which means like he was really in charge of one of the instruments that was on this thing. And I was going to go to New Zealand to visit friends when I finished my PhD thesis, which if you're not familiar with, it's a rather intensive process to finish one of those things. And he said if I finished on time, he would arrange for me to be able to fly one night on SOFIA. It has nothing to do with my research. But so we went, I wrote a piece for Scientific American. My now husband came, we were just still dating at the time. He was my photographer. So he borrowed a digital camera from my dad and went and took pictures. And then one of the things that we saw, because we went as far south and we passed the Antarctic Circle, we saw Antarctica. But then, yeah, you do see also the Aurora Australis was kind of just up there in the sky. And all the NASA people, they see this all the time. They didn't really care. But we were just like, oh my God, as tourists, this was the coolest thing ever. And here's just another SOFIA picture that, yeah, it flew around. It was like 24 staff scientists who would basically just kind of keep it on the targets that were scheduled for that night, which you actually did by literally just telling the pilot to change his course instead of steering the telescope, which is what we would normally do. So stuff like that. So anyway, it was a pretty cool experience. You have northern and you have southern lights is the point of this little story. So we have, this is a little out of order. Sorry. So one of the big drivers of what creates aurora, you don't have them all the time. As I said, this event last year was a once in a couple decades event. It was very exceptional. Is thanks to sunspots. So the sun has sunspots, which are areas where the magnetic field on the sun does not have a simple dynamo like we do. It's a plasma. It has a lot of norths and souths. And in these sunspots, you have about 2,500 times stronger than Earth's magnetic field. And it can be stronger than elsewhere on the sun. The sunspots can be bigger than the planet Jupiter. If you have protection, sometimes you can even see them. They can get that big looking at the sun. They're also cooler in temperature, and that's why they look darker to our eyes. Side note, this is the sun today. We really, really care about how it affects us, so you can actually go and look at what the sun looks like today. So you see, we have some sunspots for sure. Maybe not as big as this is these are exceptionally giant sunspots, very clear to see. And the second thing to note about these sunspots is they actually follow what's called a solar cycle. So the sun follows an 11-year solar cycle, during which the sunspot count increases and decreases. This means our sun is actually a variable star. Fun fact, it has a slight increase and decrease in its brightening every 11 years. What this means is, as you can see, we're currently at the peak of solar cycle 25. Is actually going to peak roughly next spring, I believe, is the peak. It's not supposed to be as strong a cycle, but it's really kind of a tough science to predict. And the reason this is important is something that really correlates with sunspots are called solar prominences. So these are basically giant explosions that go outward from the sun. and giant amounts of particles versus just that steady solar wind that we talked about earlier, you can have big flares of material that will get ejected off the sun. Obviously, this is a picture that we have. It was not pointed directly at the sun. That's why we can see it very, very nicely. But sometimes it happens. So what that ends up meaning is you have more auroras now if you keep an eye out on these things, looking especially toward the north. So this was last winter. I flew Portland to Amsterdam. There's a direct flight, so you go really, really north on that flight. We saw the northern lights. I was being a really a dork and staring at them. But anyway, so it's a very, very exciting period right now. We're more likely to see the northern lights than you will be, say, 5 years from now. So if you ever hear something like go out, maybe you might see it. Yes?
Why do you always see them green?
Green is just the most common color because it's associated with oxygen. And we have a lot of oxygen in our atmosphere. So yes, that's a good question, though. And then red is something more rare. So that's why I usually don't see red. But as I said, usually to our eyes, it's just kind of whitish. So the northern lights, I should also emphasize, if you hear something like go out, first of all, you should go to as dark a sky sight as you can get. It's pretty diffuse light most of the time. If you're not sure you're seeing something, actually just hold up your smartphone and do like a longer exposure. And your smartphone can often see it even if your eyes, you're not quite sure what you're seeing. The second thing to say is it's not a constant thing. Like you can go out at like 10 p.m., not see anything, go out at 11 and you will see it. So another thing, like don't just look out for 2 seconds and say, oh, it's not happening and go to bed. Like if you're really interested in seeing the northern lights. The final thing, and this is just kind of a fun one. So how strong can solar flares get? So in September 1859, we had something called the Carrington event. And this was named after an astronomer named Richard Carrington, who was studying the sun, saw that there was this giant sunspot complex on the surface of the sun. And there was actually, he saw the first time there was a flare associated with a sunspot. And it was the strongest solar storm by far in geomagnetic history. To give you an idea, so I was saying like the last one, it was like, the strongest in decades and people in Mexico saw it. I mean, auroras were seen as far south as Colombia, which is on, pretty much on the equator. Pylons, so this was the dawn of the age of electricity, but you did have some pylons. They were throwing sparks because there's so much current in the air. And they even have reports of telegraph operators. So like between Portland, Maine and Boston talking to each other for 2 hours, even though both of their power sources were disconnected. There's just so much charge in the air when this happened. So it's estimated if a similar flare happened today, we're basically screwed. It depends who you talk to. Basically because we have so many transformers that would potentially blow that it could be billions of dollars and many years until we got the power grid back online. And I mean, we have had smaller power outages. So in 1989, the entire province of Quebec was knocked out by a solar storm. Basically because there was so much current that was driven into the storm by the magnetic or the particles from the sun that it overloaded the system and it couldn't get enough in the ground in time because the Northeast is not ideal ground anyway. I have had conversations with you because obviously people who think about solar grids are also aware of this event. It's not that they're not aware of it. So there have been a lot of discussions on how you could like shield things. And so like the 1989 event, if it was a similar solar flare, we're probably pretty well protected from these things. A Carrington event, the problem is we don't really know how common they are. I mean, this was, 150 years ago. Maybe it's, every couple 100 years event. Maybe there's going to be one tomorrow. I mean, we don't really know how common these super flares are. So that's kind of one of those ones that's pretty crazy to think about. Finally, one thing that we should also note is that the Earth's dynamo is actually also unstable over particularly long times. So the Earth's magnetic field over time can flip, or it's called a reversor. And what happens is then it takes a few thousand years of a process, but north will become south at the end of that process. So the way we can tell is actually studying the movement of tectonic plates. So imagine here we have, on the Atlantic Rift, you have new ground coming out. And you're looking first at this here. So this is, 2 million years ago. You notice that this is the polarity of the material at that rift. Over time, it's going to separate. That material will be here. You will study it again, for the data from 1 million years ago, and you're going to notice it's different in terms of the polarity, what is north and what is south. And then if you look today, it could be different yet again, as there's new material that is coming upward from the magma. It is going to cool and it is going to solidify in a specific pattern. We actually know this in Eastern Oregon. There's a lava flow where they estimate that the material came out in the course of a day, and you can study how much the magnetic field changed, and it's like 6 degrees over the course of a day. Our magnetic field is just completely spinning around and it's not solidified. So this is a thing that definitely happens over time. The last reversal was 780,000 years ago. The average time this takes is about 500,000 years. So it's not like it's a clockwork thing. We basically can just say over the geologic record, we've seen it happen this many times, divide the years by the number of times it's happened, you get about 500,000. So we are overdue for a flip. I will note, whenever one of these flips happens, it's not that the north and south completely disappear for a couple of years. It's more that, so this is a NASA simulation. So if we have north and we have south, what ends up happening is the dynamo gets really mixed up. You have a lot of norths and you have a lot of souths when this particular event is going or happens. So it's you probably would definitely get, more northern lights than we normally would. It wouldn't be great for, solar particles reaching us. Humanity itself or life will survive because, we already existed 780,000 years ago as a species and we are still here. And so this period lasts for a couple thousand years. It's not quite clear how long this period takes. But yeah, basically your compass would not be useful unless you looked up that day where the poles were or something like that, because we would just have multiple. So yeah, it's kind of like for the Carrington event. You definitely won't want one of those during a magnetic field reversal. So in terms of life, we don't have mass extinction events or anything like that correlated in the record with pole reversals. But we also have a lot more tech that we did not have 780,000 years ago. So we're not quite clear on the effects of if one of these reversals were to happen today, what exactly would be the case. The final thing to point out is, the obvious question is, are we nearing a reversal? And my answer was maybe, probably not in our lifetimes. So the Earth's magnetic field is weakening over the last couple centuries. So here's a plot. If we have, the last 400 years, we have dipole strength over time. You can see since roughly the year 1700, it's actually been decreasing pretty steadily. If this remains constant, then you would see a reversal in about 1600 years. The thing is, though, this is not something you can set your watch by, and this is not a system that we understand well enough that you can predict it. This could very easily reverse, in the next day even. We don't really understand how the Earth's dynamo works. It's a very complex, very giant system. So that's something to think about, though. Yeah, so we might be heading for a reversal, but as I said, it's probably not our immediate worry. I can't guarantee, though, Carrington event, if there were to be one of those, when that would happen. Did you fix the dynamo? No? Okay, it's broken. All right, well, that's what I had for today. I'll see you guys Friday.